Dear friends, Maths Aspirants is a collective of mathematics students, research scholars, faculty members across India, started by myself in 2017, and we used to conduct several online programs to help the students who are preparing for different national level competitive examinations and PhD admissions, extra. We used to arrange online problem solving session series to help the students. As a part of that online problem solving session series, today we blessed to have Mr. Jayakumar Ravindran, a senior research fellow from IMSc Chennai. Today he will discuss some problems and some concepts about Sylow theorems and its applications. Mr. Jayakumar is closely associating with our group at least 2 or 3 years, and he used to take such sessions. I think 3 or 4 sessions have been already taken in our platform. So today's session is on Sylow theory and its applications. So I'm sure that this session will be really helpful because abstract algebra and group, especially group theory, is a very important topic in all these competitive examinations. Mr. Jayakumar is currently pursuing PhD at IMSc Chennai, and his broad research area is planar algebras. Okay, I would like to express my sincere gratitude and thanks to Mr. Jay for accepting our invitation and joining with us. And I welcome everyone to this program. Welcome, Jay.
Thank you, sir. And I'm really happy actually to be here. I think this is my 5th time, and because I'm doing it again and again because there are good responses coming from this group, and I feel like this group is more active than any other group which I'm part of, not only mathematically. Okay, so I wanted to say some things, especially today. That's why I asked Vinod sir to arrange one thing, and he arranged this thing. Okay, thank you, sir, for that. And so first we will go through the lecture, the idea of the lecture, and what is the idea of the lecture. Like, I prepared the lecture so that it can be useful for everybody. Suppose somebody, they are in first year or second year BSc, there are something they can get it. Maybe they are third year, they can get little more. If they are in first year MSc, they can get even more. If they are in second year MSc, they can get even more. But at each and every level, everybody can get. Okay, so it is kind of a test. The way I prepared the lecture using some technical idea for teaching, it is a kind of test how much you know, and that is not the important point. How much we don't know, right? The moment how much we don't know about this lecture is, let's say, 100%. Even if you are getting 30%, it will be really really good, because that is how one of my professor keep on saying that if you're having like 1/3 of the lecture or talk, you can get little bit and go for that. Okay, and I don't take notes or something. I prepare the notes, I will send it to sir. A little bit of edition needed after this class, a little bit. I will take some half an hour and I will send it to sir. Okay, he will share with you, but take some hints whatever I'm telling. At some point of time, after all the idea, it boils down into number 30, whether we can have a the divisibility or not, like those ideas. So here we are going step by step. I start something, and one particular question I'm interested in, because that question comes in the interview again and again and again, so that you might have some taste of the interview question. All other questions are not interview question. Those are asked in a previous year CSIR question. I included 10 questions. Those are easy. Additional 7 questions, those are from a recent CSIR. The first 10 questions are like before 2020. Last 7 questions are very closely related to last few years, whatever I'm going to talk. Okay, so fine. So shall I continue from the iPad? I will start. So the topic I wanted to talk about, Sylow's theorem. Already there are videos I took in this group itself. It is available on YouTube. Now the first question: what is the difference between that video and this video? That video is intent for overall group theory, then we come back to Sylows. This particular theorem with particular, I mean, the notes is intended for show the Sylows theorem and that particular question I'm talking about. So general linear question. Okay. So we'll start. So we all know about what is group, no? So I already included binary operation, but I am also including the closure to ensure that, okay, we know what is group and abelian group. No, I'm not going to touch that even though we just see. So group is a set, suppose non-empty set, and we have a operation on the group, and that operation means two element, how I can combine them, get a one element, that is a closure. So it satisfies the closure. If I am taking two element, multiply them, I'm getting into that. Sometimes I put dot, sometimes I use this. Context is clear, I don't put it like anything. Just we will leave it like A into B, like AB, like that. So it should satisfy certain conditions. First closure, then the associativity. What is associativity? Bracketing of the order doesn't matter. That is associativity. You can do BC then A or AB then C. The order matters, but bracketing order is not matter. So it's called associativity. Then there exists an identity element. And remember, the reason why I wrote this thing, because to ensure that left and right, it's not like E into A equal to A. It's E into A as well as A into E. Okay. Inverses. That means for each A, there exists a inverse unique. In fact, one can prove unique, which is also goes for left to right. This is very important. In the abelian group, you can be little bit lethargic. We can say only left exists because abelian will take care. Okay, so we know like group theory.
Sir,
Yeah. Yes.
sir, in the definition of a group, if dot is already a binary version on the non-empty set G, that
I
means
don't need to.
the closure property
Yes.
already satisfied. So why I need to mention this closure property in the definition again?
Yeah, I told you in the beginning itself. Even though that's why I underline. Even though I said binary, I just wanted to ensure the closure property in order to show explicitly. It is redundant, like it can be removed. But this actually feels like a function. To ensure extra clarity, the word I'm using closure. So in the original notes, the closure is not there. That's why I written this binary operation, tyrant operation feels like a function. Okay. So I wanted to make algebraic language. That's why this is actually algebraic language. Closure, associative. It is extra just to make sure. Okay. Okay. So we know the definition of subgroup. Mostly we are going to deal finite groups. Okay. All of my things G is the finite group. So once you understand finite group really well, one can go the complement infinite group. Okay. Subgroup means when we restrict the same, it satisfies all the four conditions. That itself on its own right forms a subgroup, and one can check if it is finite, closure is enough. Closure is enough. This is the reason I wanted to use this closure. That's why although I included binary, the word I wanted to use, the closure. So here, the function, the binary operation, not from itself. Although one can restrict, it is from G. So it is closed under that operation that is coming from. That's why I want to use closure. So closure, it's closed. That's enough for a finite set. So you have to check only the subset is non-empty, closure is enough. Okay. And for infinite set, one more condition needed. That two condition enough to say closure and inverse. And one can reduce, combine this thing and one can reduce. That's okay. These two conditions for infinite, it's enough. Okay. So we know the definition of subgroup. See, why do you want to know about subgroup? I have a structure, right? So in mathematics, we have structure, and often what happens to the structure, it is more complicated. If something is more complicated, what naturally we tend to do, we wanted to break them such a way that is useful, right? I wanted to break them, then I can rebuild it like a home, brick by brick. Okay, so there are something very hard, I can break them, and step by step I can rebuild, so that it is all understood. Okay, understood. So that's the definition of the substructure. You go to anywhere in algebra, always the substructure is very important. And we are going to put more and more condition on the substructure to get it, okay? So as I said, I'm going to deal mostly about finite groups. Okay, so finite groups, the moment I said finite group, numbers are going to play a lot of roles. That we know, right? Numbers are going to play a lot of role. So what are the numbers? Natural numbers, of course. In set theoretically, minimum non-empty means it start from 1. And I'm interested in one such kind of group is called P subgroups. What is a P subgroups? A group can be anything. A group can be anything. But P subgroup means this is a standard notation for subgroup less than or equal to. P subgroup means that is something like P power alpha. It's prime power something. P groups means it's prime power something. Those are somewhat special groups, special to deal with. Lot of ideas can be arranged in that matter. And we are very interested in maximal one. Maximal one means what? In number theory, we have a beautiful symbol like this. What this symbol means? The symbol means two things. P power alpha divides n. That means n divided by p power alpha. It's not decimal, it is a meaningful integer. Second, p power alpha plus 1 does not divide n. That means you extracted everything. If I wrote p power alpha comma m, if I write like this, the other way of saying the same symbol, GCD between m and p is 1. That means you extracted maximum, and we are very much interested in. Okay, why we are very much interested in? Because of this theorem. First, the most powerful theorem you will encounter in group theory, it's called Lagrange's theorem. What is Lagrange's theorem? In the setup of finite group, G is finite and H is a subgroup of G, then order of H will divide order of G. That is, look at this group. This order is 3 factorial. I hope that you know at least some of the examples, little bit of examples like S3. In general, Sn is n factorial. Look at this. This is like a 6. 3 factorial means 6. So Lagrange's theorem saying not possibility but impossibilities. It is easily saying the impossibility. It is a very pessimistic approach. What do we mean by pessimistic? It's a negative kind of approach. It's not saying possibility, but pessimistically it's saying impossibility. That is, you cannot have a subgroup of order 4 here. You cannot have a subgroup of order 5. So the only possible subgroups that should be devices. I'm also pretty sure that you know these things. Even though you know these things, I wanted to go through a little bit to warm up so that there is a continuity. I just don't want to go somewhere and take something, okay? So there is a continuity. So try to understand these wordings are very important. I'm using, although you know this just like information, but look at the poetic kind of wording. It's a pessimistic approach. What is a pessimistic approach? More than saying the possibility, Lagrange's theorem saying impossibilities. At least giving us some framework where shouldn't do, where should not you look. Okay, so the minimum one is 1, 2 or 3, maybe 6. That is the only possibility for this. Okay, so in the chance of prime groups, if H is a prime, then the possibility of subgroups either 0, that means identity or itself. We know about the prime number, so something about the number getting reflected. So that is a question. Now many things about the number, I don't know the group nature. When I say group nature, say theoretically there is something underlying and there is an operation. I have no idea of the group nature, but something it is reflecting. So now the question, can I extend most of the theorem about natural number here? Like Fermat theorem, there is a Fermat theorem, no? There are some other theorems like Euler theorem, like we can talk about. Now the question, can I extend them? So later on, if somebody finds somebody, you maybe get some idea about some arithmetic functions. Can I extend them to this thing? That is a natural question. Okay. So this is the first connection we have. What is the connection? The connection is, it's connecting the number theoretically to the group in a quantitative way. That is a beautiful thing. Quantitative. What is the quality? The quality of the star matters, right? The quality of the star matters. Even in non-abelian order 8, two groups are there. One is D2 into 4, another one Q8. Both are order 8, but both have a very different structure. Very different, really different structure. Okay. But here we are dealing with not in the qualitative way, rather we are trying to go quantitative way. Okay. This is the first connection, and it is a pessimistic approach. For me, I feel this is a pessimistic approach. Okay. Now let's go. The very important theorems. So the corollary is order of every element. The order of the every element. In fact, the order of the element is same as order of the subgroup is generated. Subgroup generated means there's the smallest subgroup which is containing A. Smallest subgroup which containing A. Okay. So this order of A will divide G. Another severe restriction, right? The order. You cannot get something like this. Again, this is a pessimistic approach. Why it is a pessimistic approach? So for example, I was telling about this thing. These two things are not equivalent. Okay, I was telling. One of the reason it has more order 2 element. More. This is exactly one. In fact, it is like 5 order 2 elements. As far as I could see, 5 order 2 elements are there. It is exactly one. So again, Lagrange's theorem saying not to the possibility, but it's saying that pessimistically what one shouldn't do. What one shouldn't do. That is a very important thing. Okay. So those are the reason I included these results, even though you know, most of you know these results, right? Yeah. Okay. So now this is the first thing. This is coming from Michael Artin book. One of the important theorem. I consider myself really important theorem, because we are going to do certain questions using this. Okay. So before going to this, I wanted to attend, like when I got selected in the exam, NBHM exam, I asked two of my seniors that can you train me? Then they said that yeah, we can train, but what exactly you want? I asked them that what kind of question they asked in the interview. So one of my seniors said one of the question, what is the first cyclic group which is not abelian? In a this is not the way I am forming the question is not correct. But we were understanding locally. Okay, let's form the question later. The question was intended like this: what is the first composite cyclic group? That said, that is the real question is that the first composite order where you can see that only cyclic group exists. In the prime we know. But order 6 we know that there are groups which are not cyclic in the order 6. That is the first non-cyclic groups of order coming. So we wanted to prove certain things, right? So I didn't get the idea at the time. Then I got the idea, yeah, it is something like 15. But how to prove that? This is the idea. First step, one should know about this. Okay, let's understand this. So this is the internal and external direct product idea. I have a group. Let me explain you. I have a group and I have two subgroups. The beginning of the class, I was telling no during the subgroups. The bigger structure, always scientists like to break into smaller structure, because smaller structures are much more easier to understand, much more capable, much more, really much more to understandable. So I like to break the bigger thing. So I have a two groups. Now I have a two group. Forget about this. I have a two group. Then I can form something called external direct product. And I can study, just putting the definition H and G, H dash and G dash, just like that, H dash, G dash, like that. I can go and study. This is a one way. This is not interesting. But my question is, can I break the bigger one into smaller ones? What are the conditions? If I break, so already I know externally something. Now the question, if I go like HK, just put HG such that H in H, G in G. sorry, K. Now the question, is this going to be a subgroup? The answer is no, not always. The question, not always. I have to give you the idea, right? Not always. So why not always? Just look at the simple thing. Just look at the simple thing like D 2 into 3. What is D 2 into 3? It's generated by 1 x square. This is called rotation. The x cube is identity. Y xy x square y square is identity, and the relation y x equal to y xy equal to x square. This is the relation. So here you can see that, look at this order 2. This is order 2. The total order is 6. Remember, this one is order 2. Y square is actually identity. So 1 comma y is a subgroup. Another one, 1 comma xy is again a subgroup. Can I put together and ask whether I will get subgroup or not? Okay. If I put together, what happens? If you just multiply and see that, you will get like 1 is there, y is there, xy is there. Then you will get again x square. Because y xy, you multiply y xy will give you x square. So there are 4 elements. 4 is not dividing the 6. Remember that. Now the question, sir, you are telling the 4 elements I could see, because 1 into 1, 1, 1 into y, yeah, xy, yes, 1 into xy I'm getting, x square I'm getting. Why not other elements? You just think of, okay? Try to think of why other elements are not coming. Try to think of, okay? Because there is a beautiful, again, the relation, the hk, even though it is not a, so you can ask me, why did you stop at 4? I can say that x square coming. Why not other elements? Because of this result. Even though it is not a subgroup in general, this result is saying order of h, order of k, intersection k. So it's giving me the idea. Again, can you see in this lecture, I am totally relying on the quantity, not the quality. Like the question, should I go more? No, because this telling me don't go. This is 2, order 2, order 2. The intersection is 1. So at the most you get the 4 element. Exactly, you get the 4 element. I stop. And 4 will not divide the 6. So you cannot the subgroup. Can you see the pessimistic approach? I'm approaching from a pessimistic perspective. So basically what happens that from here also you can understand. Okay, fine. Basically you understand that not always this going to be a subgroup. And the order is very nice, because I told you it's order of h, order of k by order of h intersection k. Remember, this is going to be helpful at some point of time. Okay. So now my question, when it can become subgroup? So the answer is one of them normal. If h is normal, you can relabel h into k, k into h, doesn't matter. It doesn't matter, okay? One of them, basically one of them normal. Then hk is a subgroup. You no matter, you can interchange h into k, k into h, no matter, that's a labeling. So one of them normal. Then I need to give you the definition of normal. What is a normal? G h g inverse, that is g small h g inverse, such that h belongs to h. I am fixing one g, I am changing, this is going to be h for every g. So I'm randomly taking one g, putting g h g inverse both side, and I'm seeing, and that every time when I change g, it is h, then it is normal. So one of them normal subgroup, then we are going to get. Don't worry, I'm not going to give you example of normal subgroup. We are going to get quantified. That means some quantity, the number going to help to say some group is not normal or it is normal. Okay, later on. That is the beauty of Sylow's theorem. Okay. Now let me approach from the pessimistic point of view. So at least one of them normal, then I'm getting normal. Okay, this is the first thing you should know. The second thing, suppose it is a subgroup. Now the connection, that is a homomorphism we have. We can define like this homomorphism. From this product group, this can be studied alone to G like this. This is injective. This is just a map so far. This is injective if H intersection K is trivial. Trivial, okay? I'm using one for identity element, trivial. This is going to be homomorphism if and only if. Remember, the element of H and K commutes. Okay. The elements of H intersection K commutes if and only if. Okay. This is isomorphism onto. So far, I just put like a into thing onto. Okay, onto if and only if trivial HK is this thing, H and K both are normal. So this is the thing we want. Forget first three. This is the thing. The product HK isomorphic to G if both H and K normal, intersection is trivial, and this is a full group. Remember, both, forget about first three. Both normal, intersection trivial, the HK is to be whole. This is what we are going to do. Okay, this is the 20% of understanding. So like 25% of understanding. Now we are going to the next level. Okay, next level means Sylow's theorem. Step by step, I am going to introduce you Sylow's theorem. So far, any questions? Can I continue?
One time repeat result D.
Okay, result D, I want to repeat. Okay, so let me erase here. So we are going to use result D again and again. Most of the questions, very important. So is it finite or infinite? Doesn't matter. I have a G, the set of H and K inside G. Then I can study H cross K alone. This is the external studies. Treating H as a group alone, K is a group alone study. That is an external approach. Internally, I have a set. Now the question, when this is isomorphic to G itself, because that is the where I start. Something I'm getting subgroup, I don't like it. So now the question, when it can be equal to G. So the first condition, both normal. Second condition, HK to be G. It is a subset. It should be equal, improper subset. Third condition, H intersection K equal to trivial. That's it. If that thing happens, this three thing happens, this is true. H cross K isomorphic to G. That's it. If the three things happen, we will see some example. Both normal, HK should be the whole. And remember, this is going to help us. HK. Finite setup. This is going to help us. All of them are today quantity oriented, no quality at all. Okay. So both normal. This is also we are. So for example, this is also going to be catched by this quantity. This is already a quantity number, just one. Trivial. Like I can put it like order is one. The cardinality is one. Like that I can put. This is also going to be quantified. That is the where Sylow is going to work. The Sylow's theorem. That's why they named. Okay. Shall I continue?
Yes, sir.
Yes. Okay. Now we have three Sylow's theorem. I will quickly go through one by one and directly start problems. So before going to the Sylow's theorem, we need to set up something. What is the setup? As I said, we are going to only look the quantity. Suppose my group is order n. I am also going to consider only finite group. This is my group and which is order n. I wanted to set up. So Sylow's theorem, basically, let us talk a little bit. The Lagrange's theorem says I have a subgroup of a finite group. Then the order of the subgroup divides order of the group. The question is that, okay, fine. I know that it is a severe restriction. For example, I will take like some group of order 12. and 6 divides 12, like number, can I get, in general, can I get order 6 subgroup of G? It is not true. It is not true that always you get it. For a given any divisor of the order of the group, can I get some subgroup of that? No, it is not true. It is not true always. Okay, so it is not only a pessimistic approach, it's a very number theoretical approach. It's going to give a necessary condition only. So now people ask the question, at what level it is true? At what level, in the sense, it should be true up to some level. That's why the Sylows, that is the point Sylows thought and gave the idea. So Sylows saying that it is may not true for a general thing, but particularly it is true. He's saying that pick 1 prime, okay, 1 prime which is dividing. Now take that maximum out, that is p power alpha dividing n, or p power p and the m is 1. Both are same, okay. Take the maximum. Like for example, I work with 96, 2 power 5 into 3. Suppose 12, it is 2 square into 3. Okay. Suppose 56, 2 cube into 7. So you split in that way. Okay. We also kind of internally assume small prime comes first, larger prime go like later, like 30. So I'm going to be 2, 3, 15. 5, sorry, 5. 2, 3, 5. So we are kind of understanding in this way. Okay. So Sylow saying that pick a 1 prime, split that. For example, if I pick this prime, I should write like this. So that the 2 and 5 common GCD must be 1. Pick a prime. Then he's saying that first Sylow theorem says that there exists a subgroup. This symbol stands for there exists. There exists a subgroup in G such that order is p power alpha. Call such subgroups, remember the English, as Sylow subgroups. So the first theorem, it is an existence theorem. You have to have some object to work on, correct? You have to have some object and work on, correct? So first theorem says that whenever there is a group, you split like this, pick a prime, split like this, take the maximum. So there exists a subgroup, definitely, at least one group. There may be plenty. There may be plenty. At least one subgroup that order. This is the first Sylow theorem, okay? So let G be the finite group of order. I used p power n, their alpha doesn't matter. G contains at least one subgroup of order p power n. If you do it like this, okay? I used alpha there, okay, it's fine, no problem. Here I don't even mention n. When you split the group into like this, we have a group, pick up prime, p power n into m, where p and m no GCD other than 1. Then there exists at least one subgroup. That is existence. So now we have something to work on. Now what is the obvious question? Once I have something, at least one, mathematician always look for a uniqueness, right? So unfortunately here there is no uniqueness, but still we can say something. How many? Suppose that is not unique. More than one is coming. How many? So that is the second Sylow theorem. The second Sylow theorem says, same, write the group like p power n and m. Forget about the p power alpha business. P power n is good. Like this, then I have a one Sylow, another p Sylow. Suppose I have a two different. The second Sylow theorem saying that there exists a G where this happens. That is, in another word, so let me rephrase it in a right way. You find one Sylow, okay? The second Sylow saying that giving idea to get all of them. You get the one Sylow. Put G before, G inverse before. And where is the G? These are called conjugates. You take a subgroup, put like this by G, these are conjugated by G. All Sylow will come included. That is, I have a one Sylow, conjugate them, conjugate them, conjugate them. You will get everything. That is, in another word, two p Sylow subgroup of conjugate. I have a one p Sylow, I have another p Sylow. Then there exists a element G which conjugate them. So I'm telling the same thing in a various way. You get one p Sylow. The first one saying at least one. This is we are going to this version we are going to use. We are getting one Sylow, conjugate that. You get everything. You get everything. Similarly, in other words, you have a two Sylow. From one you can to go to other by conjugating. This is the second Sylow's theorem. Okay. Second Sylow's theorem. Okay. Third Sylow's theorem. So let me show it. Okay, there is a corollary. I will come back. Third Sylow's theorem is a very beautiful theorem. This is the where we are going to start. It's saying that the number of p Sylow subgroup divides the m. I start with n. I start with the group order p power n and m. Let us denote n sub p, subscript 3, like number of p Sylow subgroup. Then that will divide the m. In Joseph A. Gallian book, they would say that it will divide overall n, but this particularly m. They will say they divide all. But Michael Artin book, they will particularly say m. This is very important, okay? And n p congruent to 1 mod p. These two conditions should necessarily satisfy. Again, it is a pessimistic expression. It's giving some idea that how to count how many. See, this is the way, this is the point you should understand, because the corollary we are going to make quality into quantity. Somehow we are going to make a number theoretical thing. Okay. So let me explain this. We start from a group. The first theorem says existence. That's it. Second theorem says they are conjugate. The third theorem helping us to count. It's not going to say exactly, but giving some idea. If such a number exists, it should divide the m. It should be divisor of m, number one. Also, it should satisfy this condition. What is this condition? P divides np minus 1. Okay. So now let's go to this place. Somebody asked me that, can you repeat? At that time, I was telling this is going to be quantity because of this. Okay. Because of this idea, this becomes going to be quantity. This is already a quantity. This looks like a quality, but I said that I will make it quantity. Okay. Okay. What is that? The corollary. Second Sylow's theorem says that the corollary says that Sylow p subgroup is normal if and only if unique. That is np equal to 1 if and only if that subgroup is normal. You are going to get one subgroup if it is normal. Normal means 1. 1 means normal. Now it becomes a quantification. So now let's start working on the questions. Okay. So what is the first theorem? Existence. Second theorem, conjugation. The corollary says that unique if and only if normal. The third theorem says that how to count, giving the idea, how to count them. So this three theorem, we are going to start from here, slowly come back, and we are going to use this idea. What is the idea? Product group. The product group says both normal and HK should be the full group and intersection should be trivial. So we have all the quantitative idea. So let's see. Right now, it may be difficult for you to put it, but if we start working on the example, it will be easy. Okay, let's start working on the example. Okay, so give me a moment. I will add one more. There I am. Give me a moment. Put it. Okay. So we are going to work on one example. What is the example? One example.
Sir, you can repeat the Sylow-second theorem once again.
Okay, I will do it. The Sylow-second theorem says that the corollary is more important than this. I have a H1, I have a H2, 2p Sylow, 2 related to the single prime, 2p Sylow, okay? Then what is the relation between them? There should be some relation we are getting. So what is the relation? One is conjugate of other. There exists a G belongs to G such that one conjugate to other. In other words, in other way, you find one, then before and after put G and G inverse, vary the G, you get all. This is what it's saying. You get one, before and after you put G and G inverse and vary the G and you get everything. Okay.
Okay, sir.
The corollary is very important. What is the corollary? NP is 1 if and only if that Sylow normal. So normality we got in terms of questioning, like the numbering. Okay, let's see. Once we start working on that, we'll understand. Now I can write like 3 into 5. Then I can work on. How can I work on? First I'm looking for 3. When I go for 3, what is N3? N3, okay, sorry. Sorry. Yeah. N3 congruent to 1 mod 3. That is the condition. NP congruent to 1 mod P. Okay. NP divides M, the remaining. N3 will divide the remaining. What is the remaining? In our case, 5. So this is 1. This is 5. There are two possibility of divisor. What are the divisor? It can be 1. It can be 5. So 1 is always a possible. Look, put it here. 1 minus 1, 0. 0 divisible by 3 is correct. But 5 is not possible. Put it here. 5 minus 1 is 4. Not divisible by 3. So it is not possible. So we are getting N3 equal to 1. So normal. That means normal. Very good. Now N5 congruent to 1 mod 5. Remember again. NP congruent to 1 mod P. Then N5 will divide the remaining. Okay. That is same as I can put it like this. N5 divide the remaining. What is the remaining? 3. So the answer can be 1. The answer can be 3. From this, I am getting the divisor, possible divisors of 3, 1 or 3. 1 is always possible, but 3. 3, if I put it on this thing, 3 minus 1 divisible by 5, it is 2. 2 divisible by 5 is not correct. So, so N5 is 1. That says that if you take a H of order 3, first Sylow's theorem saying that there exist. First Sylow's theorem says that there exist both normal. Correct? First conclusion. Why? Because of this one, both normal. Okay. Then what is the order? Second, order of H intersection K is trivial, is 1. Sorry. It is 1. Why? Because it is related to 3 prime. You could say that the GCD between 3 and 5, because H intersection K is a subgroup of H, is a subgroup of K. So it should divide 3 as well as 5. So that says that it can be 1. Other than 1, it's not possible. That is one way of saying. Another way, the H elements are related to 3. The K elements are related to 5. So they are two different things. Other than identity, they cannot have a common. They cannot have a common. So it says that clearly both normal and the intersection is trivial. The third one. What about the HK? One of them normal, it's going to be group. Even though it is not group, doesn't matter. Order of H, order of K, order of H intersection K. which is 3 into 5 by 1, which is 15. So this says that HK is full. Correct? So we are getting all the three, both normal, the HK is full, the trivial, that implies G is isomorphic to H cross K. That is the thing, no, we saw. So let's go back to that thing. What we want? Here, both normal, HK is full, and it's a 1. That means trivial. H intersection K. These three things are there. If that three things are there, we say that H cross K is isomorphic to G. Okay, very good. So we are getting both normal, intersection is trivial, that is order 1. Because of this quantification idea, we can see that we can get 15. So I should have put it in this order, but I wanted to calculate this, that's why I put it in 2. Okay. In that, it's order like both normal, full group, and the intersection is trivial. I calculate the intersection in the second way because I wanted to use them here. So the order of G is 15, order of HK is 15, so it's equal. And now you can see that this is order 3. Order 3 is a prime, which is equal to Z3. This is equal to Z5. And Zm, Z10 isomorphic to Zmn. Very easily anyone can do that. Is 1. That says that order 15. See, can you see from unknown to known we are coming? Just using the order, from the unknown to known we are coming. Look at that, G is unknown. We know only one information. What information? It's order 15. Finally, we conclude that it must be cyclic. This is the question they asked in the IMSc interview for him. Starter question. This is the first time a composite number, really a composite number. Yeah, there are prime, like 2 prime, like not exactly composite. So 9 is also composite. 2 square is 4 also composite. It's kind of a 2 prime involved. P and Q, per P less than Q. It's not like a P square, P less than Q. Still, this is like a, cyclic. So one can try to generalize this thing to abstractly for any PQ. You will have some problem. One of them will turn into 1, another one we will have a problem. For example, look at 21. Let's start the same idea with the 21, okay? Let's start with the same idea with the 21. If I start with the 21, what is that going to happen? 3 into 7. Now look at 3. N3 congruent to 1 mod 3. At the same time, N3 will divide the remaining. So the possibility is 1, 7. So 1 is always possible, but 7 is not possible or not. 7 minus 1 divisible with 3. So maybe possible, maybe. 7 minus 1 is 6, divisible by 3, remember. Okay, let's see this side. N7 congruent to 1 mod 7. N7 will remaining 3. So the 1 or 3. And 1 is always possible. What about 3? 3 minus 1 is 2. 7. Whether the 7 is divisible with 2? No. So N7 is 1. So one of them we are getting 1, another one we don't know. So there are 2 cases. If the another one is also turned into 1, we could directly say it is abelian, cyclic, directly. Same idea we can use, product. Both of them 1, so normal. Then we can calculate everything here related to 3, everything here related to 3, everything related to 7. So the intersection is trivial. And you calculate HK. It's HK. Because intersection trivial, there is no HK. H intersection K. So it is 7 into 3, it is 21. So full, we can go. But the problem, what happens to the 7? Okay, we have to deal. That means this indicating order 21 may have some non-abelian thing. Maybe non-abelian thing, right? If it is abelian, things are okay. It's indicating as something or non-abelian. Okay. Okay. Even for simpler group of order 6, look at 6, N2 and N3. You can see the problem. The N3 will turn into 1 after calculating. N2, 1 or 3. There are two possibilities, and both possibility exist. The first possibility is saying cyclic. The second possibility is saying that it cannot be a abelian. So there is an idea that you can get non-abelian group. In fact, there is a non-abelian group, no? S3. So this is possible. So one have to be very careful. That is what I was putting here. So 15 we worked on. 28. Okay. So let's say something about not simple. Not simple means it has at least 3 normal subgroups. One normal subgroup is trivial, another normal subgroup is full, the full group. So I will say a group is not simple. That means it has a normal subgroup which is not a trivial one, which is not a full one, which is something in between. Okay, it's like a maximal ideal kind of thing. Something in between. So what is the definition of a simple group then? Precisely 2 normal subgroup. We don't consider the possibility of, the trivial group is a trivial, so we don't consider. Precisely 2 normal subgroup means simple. More than 2 normal subgroup means not simple. Do you understand that? Can we continue? Okay. This is my IIT second level exam question. IIT Madras, after this GATE, NET, I gone into exam, second level exam. They asked me this question. Prove that group of order 45 is abelian. Prove that the group of order 45 is abelian. Anyway, I'm going to give you the notes. You are going to understand this 28. Let us do the 45. I'm going to give you the notes, no problem. What is a 45? How can I split? Please help me. Interaction. Step by step, help me.
3 square into 5. 3 square into 5.
3 square into 5. So I'm going to based on 3. So N3 congruent to 1 mod 3. And N3 will divide the remaining 5. So that is a chance of 1 or 5. So what is the answer? 5 minus 1 is 4. But that is not divisible by 3. I am putting this into here. I can see that is not possible. Okay. So now I am based on 5. N5 divides 3 square. Remember 3 square, not just 3, which is 9. So the possible number is 1, 3, 9. 1 is always possible. What about 3? If I put 3, 3 minus 1 is 2, not divisible by 5. 9 minus 1 is 8, not divisible by 3. So not possible, not possible. This saying that N3 equal to 1, N5 equal to 1. So the first theorem, I can always get a existence. I can always get a existence. Sorry, here 3 square, which is 9. Remember, this is not 3, the maximal 3 square. Some of the people deliberately do some mistakes, okay? I mean, not deliberately, they don't know. So we are getting 1, we are getting both normal. Both normal. And you can see that intersection is, second intersection is trivial. Why? Why trivial? Because something is related, the H is related to 3, prime 3. The K is related to prime 5. They cannot have a common. Every element is related to prime number 3. Every element in K related to prime number 5. So they cannot have a common. The third one, order of HK, which is order of H, order of K. What is that? Order of H, order of K. Order of H is like 9. Order of K is 5, is 45. So it's full. So that says that G is isomorphic to HK. Same routine. Again and again it will come. H cross K. But what is H cross K? H is like 9. You know that P square is always abelian. P square is always abelian. Cross Z5, abelian. Product of abelian is abelian. Some of the things may be not clear for you because you may not have a understanding of that sort. That's okay. So for example, I am saying that product of abelian is abelian. In this class we cannot do, but note it. This you go and study, you will understand. So sir told us product of abelian is abelian. So is it true? Just go and search. That is how the curiosity created. And why product P square is abelian? Class equation, from the class equation. Then you have to develop the question you ask. Okay, why P square is abelian? So 3 square is abelian, 2 square is abelian. Why it is? Then you will start the understanding of class equation. Sylow's theorem done after the class equation. Okay, so this is my IIT question. Just like that. One of the question. Only you need to answer 5 of them to get selected. One of the question is this. Okay. Okay, fine. Shall I continue?
Yes, sir.
Okay. Fine. So far we got some idea. So what are, let us summarize. What are the things we saw? We saw about Sylow's theorem, right? We saw about Sylow's theorem, right? Very good. Step by step we are going. Before the Sylow's theorem, product group idea, the one of the important thing. Okay. Then before that we saw like what is so some of the thing, what is simple, what is not simple. At least you know how to work on. The first step about Sylow's theorem, what? So let's go for some question. Before I'm coming to this, let's go for some question. Here I included 10 very important CSIR coming question. See, we proved much more today. Prove that any group of order 45 as a normal subgroup of order 9. We proved much more. We proved abelian itself. So suppose somebody asking this question, you should stop at the point of what you do. They are asking about 9. Basically, they are asking you to tell you about 3 Sylow subgroup. Correct? You have to go from the 3 Sylow subgroup. Correct? So you start 3 Sylow subgroup, calculate N3, you will find it 1. So this question is answered. This question is answered. Okay. G, determine the possible 7 Sylow subgroup. This question we answered, no? N7 is actually 1. N7 is actually not 1. N7, no, we have to answer. So how to answer this? 21. You just go for 21. 3 into 7. They are asking only 7 Sylow. N7 congruent to 1 mod 7. N7 divides 3. So the answer is 1 or 3. So that implies N7 can be 3 minus 1. So 3 minus 1 is not possible. Divisible by 7. So N7 is 1. So this question answered. Okay. Let G be a finite group and P be a smallest in this one is odd. This one is odd. At least in this class, I don't think so I can do it. Okay. This one is you can try. This is not exactly a group Sylows related, but even though I just included to see if you solve this kind of questions now, you will get some non-abelian group ideas. That's why. So the answer is actually the number of elements of order 5 is actually how much? P5. So that's not a relevant question anyway. I put it. Okay. So the question. Can somebody read the question?
Is the alternating group A4 simple? Justify your answer.
Okay. The question directly pointed to some particular group, like particularly, very particularly. What is particularly? Like A4. So if you ask me, I rather go generally. What is the order of A4? Which is 4 factorial by 2, which is 24 by 2, which is 12. I wanted to analyze the 12. Okay. So I have a G. What is 12? 2 square into 3. Good. Now I can think of n2. n2 congruent to 1 mod 2. n2 will divide the 3. So the answer can be 1 or 3. Both possible. 3 minus 1 is 2. 2 is divisible. n3. n3 congruent to 1 mod 3 by third Sylow's theorem. n3 will divide the remaining 4, remember, which is 4. So the answer can be 1, can be 2, can be 4. So 1 is possible, 2 is not possible. 2 minus 1, if you put it on this equation, it's not possible. But on the other hand, 4 is possible. Now we are in the situation. What is the situation? Situation n2 can be 1 or 3. n3 can be 1 or 4. We are in the situation. So the cases can be like n2, n3. So the cases can be like 1, 1, both possible. Suppose I have a group 1, 1, okay. 1, 4, that's also okay because we are getting at least 1. 3, 1, 3, 4. There are 4 cases, right? Look at the possibilities. So 1, 1 is possible. That case I'm done. I wanted to say something like generally I'm doing, not only for A4, any group of order 12. In this case I am done. In this case also I am done. In this case also done because I am getting at least one Sylow subgroup which is unique. If I am getting one Sylow subgroup which is unique, automatically normal, and there are other primes involved, that group, so first of all, that is not trivial. Why? Prime number involved, minimum 2. The second thing is that is not full because other prime numbers are involved in 12. So in this 3 case, I am done. I have to only care about this case. What is the case? n2 equal to 3, n3 equal to 4. I will give you a small trick. Suppose we let's analysis. What is the biggest prime? 3 is the biggest prime. So that is better to start from there. Suppose the case true. Suppose true. This is a second level of trick, advanced level of trick. Let's take K1, K2, K3, K4. Let's take K1, K2, K3, K4. All of them are 3 Sylow subgroups. There are 4, right? There are 4 3 Sylow subgroups. That's okay. So how many of them there are element? 1 identity element plus 2 element. Am I right? From the first subgroup, I'm going to get 1 identity element, 2 other element. Am I right?
Yes, sir.
Yes, sir.
Here I'm going to get 2 more element. Why I'm going to get 2 more element? I counted the identity element. Okay, identity. I accounted the identity. So 2 more element, 2 more element, 2 more element. So totally 9 element. Now the question, first question. You counted 3 elements, that's okay. You counted 2 elements, but why there is no repetition? I can count something like a repetition. No, it is not repetition because these 3 elements, other than identity, 2 elements are repeated because Ki intersection Kj is trivial. Sometimes I use E, sometimes I use 1. Just adjust with me. When I not equal to J. Why? You know Ki intersection Kj is a subgroup of Ki as well as subgroup of Kj. Both divide the order, no? So suppose let's say K1 and K2 something in common, more than identity. Then that divides K1. But K1 is a prime number. So it should be equal to the intersection should be equal to the K1. Similarly, it will divide K2. So the intersection should be K2. So that's why there is no element between K1 and K2. In fact, no element intersection between K1 and K2 other than identity. That is the reason we are getting counting. So 9 element I
Hello,
counted.
sir.
Yeah.
Sir, sorry to interrupt. Can you please repeat this explanation, sir? Like why K1 intersection K2 is.
Yes. I will do it again.
Yeah, sure, sir. Thank you, sir.
So now we are in the case, no? Case n N2 equal to 3, N3 equal to 4. I told you take K1, K2, K3, K4. And remember that Ki is actually 3 Sylow. 12, we are in the 12. 2 square into 3. I'm going to get one identity, 2 more elements. The Ki intersection Kj, I am saying trivial, where I not equal to j. Why? Because Ki intersection Kj sub of Ki and Kj. And remember the 3, the prime is very important. So order of Ki intersection Kj will divide order of Ki as well as order of Kj. But this is 3. If it is more than 1, suppose this is more than 1. More than 1. That implies it should be 3. That implies Ki intersection Kj equal to Ki. Am I right? That says that Ki inside Kj. And this is also 3. This is also 3. That implies Ki equal to Kj. Now is it clear?
Yes, sir. Now it's clear, sir. Thank you, sir.
So that's why there is no intersection between any of them if I not equal to j. So I can count other than identity. I can count 2 more element. I can count 2 more element. I can count 2 more element. Totally 9 element. 2, 4, 6, 8 plus identity. Now here the complex 7. This is just not a prime square. We have to handle a little more carefully. Here how many I am getting? H1, H2, H3. This H3 we are not going to care, but okay, H1, H2, H3. H1 identity, sorry. We calculated already identity. I'm not going to calculate the identity, but remember that what is the order of HI? Sorry, some problem. Yeah. What is the order of HI? HI order is 2 square, maximum 4. Remember. So HI going to give me 1 identity plus 3 more elements. I don't count the identity. Already I counted the identity, no? So the H1 going to give me that. H2 is different from H1. Do you agree? H2 is a different from H1. That's why we are getting. So there exists at least an element in H2, not in H1. Why? They are same order. They are same order. So there must be some element in H2 which is not in H1. If every element in H2 is a part of H1, they must be equal because they are the same. 4. So there is a element. So that will contribute 1 more. So initially 9 plus 3 plus 1, which is 13, more than 12, more than the group order contradiction. Now the question to get the complete answer, you can ask 9 you counted. Why not this 3 already counted? Over counting happens? No. Why? These are related to 2. Every element related to 2, which is inside H. Here the every element related to the 3 prime. So those order are different, these order are different, so that is not a over counting. Here 1 more element coming because H2 is not H1. Fine, you got the idea? So this is a contradiction. This contradiction happens. This contradiction happens because we assume N2 equal to 3, N3 equal to 4. So no such case. There is no such case. To practice this method, this is called a counting method, negation by the counting. Throughout this lecture, can you see I am a very pessimistic. Pessimistic means I am very interested to say not happening. Remember that pessimistic not means negativity. That is not true. Pessimism never means negativity. Pessimistic means impossibilities. You search for impossibilities. Okay, it is not a bad word. Okay, pessimistic. I'm really pessimistic. Okay, so if it is not happening, only other cases 1 1 1 4 3 1, and this is not happening 3 4. So all of them you got at least one Sylow, which is unique, hence normal, proper, non-trivial. Yeah, we are done. So at least after this class, okay, at least after this class, what is the idea? Whenever you face exam questions like a quantity, they are giving only the quantity. Start doing the Sylow analysis. Then there are tricks. Okay, if you know group theory, sorry, group actions, I could tell you one more thing. Okay, this is the theorem we gone through. Okay, determine all subgroup. You know, this is also not exactly related to Sylows, but it can be done through that. Prove that every group of order p square, this is a class equation. We are not going to do it. This is a class equation. The 10th one, can somebody read the 10th one? 10th. I included the 9th question just because of I am using at some point. That's why I included. Go for the 10th one. Read someone.
If G is a group of order 30, show that G has a normal subgroup of order 5.
So G as a group of G is a group of order 30. Show that G has a normal subgroup of order 5. Specifically, they are asking this question. What to do? We need to start basically. So we need to start. Let me erase this. The question specifically asking only the quantity based, not a quality. G 30. 30 can be written as 2 into 3 into 5. Am I right? Am I right?
Yes, sir.
So they are asking only for N5. We will go like this. Mod 5. The N5 will do the remaining. What is the remaining? 2 into 3. Put it in the way. It's like 1 or 2 or 3 or the combination. Okay, that's very important. 6. There are 4 possibilities. It is actually 6. Divisors of 6 can be 1, can be 2, can be 3, can be 6. So 1 is always possible. That's okay. That is what we are intent to prove. If it is normal, I want the answer. 2 is not possible because 2 minus 1 not divisible by 5. 3 is not possible. 3 minus 1 not divisible by 5. But there is a problem. Look at 6 minus 1 is divisible by 3. Now we are getting the problem. How can I solve? Now the question, no? How can I solve this? So what is the idea? Like, the problem 6 minus 1. So let us start. Only method we know so far. Let's start counting and see some problem. Whether something helpful. So what is the idea? I wanted to prove this. But 6 is a possibility. Let us see. Suppose N5 is 6. Then what happens? I have a H1, H2, H3, H4, H5, H6. This is the only method we know. I will count 1 plus, this is a 5 order, 4 element. Here there is 4 element, 4 element, 4 element, 4 element, 4 element. Why these are 4 element? Because identity I counted 1. And I'm getting 4 element. Why? Because HI intersection HJ is trivial. If I not equal to same argument because of prime. If HI intersection HJ is not trivial, then it must be whole because 5. Same argument. That's why I'm getting this many elements. So totally 1 plus 6 times 4. The answer is 25. Am I right? Fine. Can I continue?
Yes, sir.
So this is the where I am stopping at. So now still, even though the question being asked only in terms of 30 and they are looking only for 5, we need to go through the other element. What is the next biggest prime? The next biggest prime, the next one, 3. So n3 congruent to 1 mod 3, n3 will divide the remaining 2 into 5. So it can be 1, it can be 2, it can be 5, it can be 10. Similarly, go for that. n2 congruent to 1 mod 2, it will divide remaining 3 into 5, it can be 1, 3, 5, 15. All of them are possible. That is a problem. In n2, all of them are possible. In n3, you can negate something. Like 2 is not possible, 5 is not possible, 10 may be possible. Here, everything is possible. That's a problem. Now, already we are in the case n5 equal to 6, 25 element counted. When I go here 1, suppose if I go here 1, that k order 3, okay, the k order 3, correct? The k order 3. This k order 3 will contribute 1 plus 2 element. 25 already counted. Now I'm getting two more element. Identity counted. Suppose it is 1. Suppose it is 10. We are done. Suppose it is 10. What happens? K1, K2, K10. Here I will get 2. Here I will get 2. Here I will get 2. Same idea. So there are 20 more elements will come. That is not possible. So this forcefully saying that this must be 1. So it is not possible. So in this case, this is not possible. Okay. Now let's come back to it.
How
Yes.
do we know that these will be unique? Now that we're talking about n3 instead of n5. How will we know that the elements of
Very
n3?
Good question. Okay. The question really, did we overcount it or not? Correct? Do we overcount it? So from the theorem, directly we just thrown away 1. Only possibility 1 or 10. Already we have taken the situation, the case n5 equal to 6. The choice is made before n5 6. In the n5 6, remember we are in the 30, 25 element already accounted. Suppose it is 10. There are two cases, 1 or 10. Suppose 1 we will continue, but suppose 10. That means K1, K2, K3, K10. And remember this Ki is order 3. And they do not intersect, right? Ki and Kj intersection is trivial, no? The trivial intersection. That's okay, right?
Yes, sir.
Trivial intersection, correct? It's
yes, sir.
Prime, not cyclic. That's not the correct reasoning. Cyclic, not prime.
Yes, sir.
Prime, they're prime. That's the important thing, not cyclic. So that means identity I already counted, and all these 25 element other than 1, 24 element are related to H, which is a 5 Sylow. Hi is 5. So it's related to the 5. All the order of the element is 5. Exactly 5. Non-trivial element order is 5. Here the non-trivial element order 3 because it's related to 3. So that's why I'm going to get 2 more element. 1 identity. There are other 2 element which is order 3 element. So 2 more element. From here other 2 more element. From here 2 element. Like that 2 element. So 20 elements. Now it's clear?
Yes, sir. We get Ki. Yes, sir. We get Ki intersection Hi is also E.
Yeah, because which is common divisor. Ki intersection Hi or Ha, whatever, it's actually a common divisor of 3 as well as 5, correct? Because subgroup,
Yes.
the order. So that is not possible. 20 plus 25 is more than 30. So it is not possible. Not at all possible.
Again, that prime reasoning we are applying to K
Yes,
and H.
same prime.
Earlier we just applied it within K. Got it.
Yeah. So n5 6 directly implies forcing my n3 to be 1. So only 1k. That is a very important observation. Okay, let's see what happens to this. So if it is 1, suppose this is 1, it's going to give me 2 more element. Already 25 plus 2 more element, 27. 3 more things I need to have, right? 3 more things I need to have. Okay, 3 more things. What is the 3 more things? That should come from here. If n2 is 1, suppose n2 is 1, what is the problem? The problem, suppose let's say hk, yeah, okay, let's take L. The order of L is 2. 1 element for identity, 1 element I will come out of this, but still 28. 2 more elements I need to get, correct? 2 more elements I need to get. So that means n2 equal to 1 is not possible. n2 actually 3 is possible. So that means L1, L2, L3. From L1 I will get 1 element because order is 2. From this I will get 1. From this I will get 1. So that is identity 24 order 5. Order 3. How many elements? 2 elements. This is order 1. Order 2. I'm getting 3 elements. So totally 24, 25, 5, 30 elements. Now we are accounted. So this is forcing me to choose not 5, not 15, only 3, not even 1. So finally we got the idea that n5, if it is 6, if we take, that forced me to take n3 equal to 1, n2 equal to 3. Still we are not getting, like, yeah, so we wanted to prove exactly 1. We like to prove exactly 1. What happens? We are not getting, somewhere some problem is coming, but here the matter. Look at, here the matter. The n3 is 1, correct? The n3 is 1. The moment n3 is 1, it is a normal. Now we are going even deeper. Very powerful PhD trick. n3 is 1 implies the k is normal. K is normal implies hk is subgroup. Am I right? K is normal, right? hk is subgroup, right? This
Yes,
is
sir.
very important trick. I don't think so you can get it easily. Please pay attention. This trick is not just, I never told anyone about this trick. I never taught this trick. Okay? Especially I wanted to teach in this class. Nobody knows. Only very high-fi PhD people know. From IASC, from IMSc, TFR, they know. I will teach you. So n3 equal to 1 says k is normal. So hk is subgroup. What is the order of hk? Order of h, order of k, order of h intersection k. So this h I am taking one of the silos. Okay, take one of the, take h equal to h1. Just take one of the silo. Okay, not a problem. One of the silo. So what is this? The order 5, order 3, order 1. So 15. 15. Can you, if you are really preparing for the exam, just tell me something. Just 2 number. This 2 number. Can you say something about the hk? hk order is 15.
Normal.
Why normal? Yes. Why?
Index 2.
Very good. That's the thing. Index to normal. That is a beautiful thing. So hk is normal. This is a standard definition. Normal in G because index 2. Because index 2. And it has h1. Normal means what? G hk G inverse is again hk. That is the definition of normal. And we know that take one silo, conjugate it, every silo will come. That you know, right? Take one silo, by conjugating, everything will come. So the first silo inside here, H1 inside HK. That is how we created. H1 is H, both are same. Now I'm conjugating randomly this H1, which is inside the conjugation, correct? Which is nothing but HK by normality. So that implies all Sylow phi subgroup inside HK. Impossible. Those are 24 elements are there, including that 25 we calculated. This is 50. Now it is possible. This trick I never seen anywhere. I never told anyone. Only few people knows. You see, this is called playing along. I will again go through. The case the question is asked in terms of numbers. So what is the first step we need to do? We need to do Sylow analysis. I'm hoping they ask me to prove normal subgroup. I'm hoping I will get normal subgroup, right? I'm hoping. I don't know. I'm hoping. But when I analyze this really, I'm not getting. I am getting another possibilities. What is the another possibility? The another possibility, what happens that N5 I'm calculating. Okay. Okay, sorry. Here. 30, N5 I'm calculating. It can be, it cannot be 2, it cannot be 3, but it can be 6. I want exactly the answer 1. I wanted to understand what if the 6. Only method I know so far, if it is not direct, now I go for the counting. When I go counting also, I'm not getting. So when I go counting, I'm going counting. That forces this to be 1. That forces this to be 3. I'm getting perfectly. What is the perfectly? Order 1 is 1, order 5 is 24, order 3 is 2, order 2 is 3, so 30. I'm getting perfectly. I'm over. I thought that something go extra, so that I will say something go extra more than 30, I can contradict something, but perfectly. Even though that is a perfect thing. That one gives me idea. So in this right now the moment, insert in your memory. Okay, insert in your memory. Just stab it in your memory, inject in your memory. Whenever Sylow P subgroup is unique, that is going to tell you lot of ideas, right? That's what I'm using. So when I take the choice of N5 is 6, that forces N3 equal to 1, N2 equal to 3. But I'm not interested here. I'm interested here. That says that it is normal. Then I can compare the subgroup, and that subgroup tend to be 15, and that tend to be index 2. Index 2 are normal, and it contains, normal means what? It is invariant under the conjugation. It is an invariant under the conjugation. So I take 1 and go like this. Then all the things, all Sylow 5 goes inside. But that's not a possible, which is 15. How can something can accommodate? Am I right? 15, how can it accommodate something like 24 order 5 element, which is a contradiction? Why this contradiction happen? Because we assume this is 6. So then, so such a case not possible. Do you get it? The last part?
Hello,
Yes.
sir.
Yes.
Sir, in that, like in the middle step, you put H is equal to H1.
Yes.
It's a subgroup of HK, which is a normal subgroup of G. Sir, I have
Not,
doubt like
not H1. K is a normal subgroup.
H is a subgroup of HK, right, sir?
Yes, H is a subgroup of HK, right?
Sir, like if HK is a subgroup, then H and K are subgroup of HK. Is it true?
Correct.
Okay.
H
So by using
inside HK, K inside HK.
Okay. So HK is a subgroup means H is also subgroup of HK and K is also subgroup of HK.
Yes.
So by using this fact, you finally arrive that HK is a subgroup of order 15, but it has an element of 25, which is a contradiction, right?
Yes. So I'm using various facts. First of all, HK need not to be subgroup general. To HK become subgroup, we need at least 1. That is the reason I taught this. Give me a moment. That is the reason we gone through this product. H is a normal, then at least one of them, okay? At least. I was saying at least one of them. If both of them normal, we can split them. If one of them normal, there is something called semi-direct product that we can talk about, okay? Fine. So you got the idea?
Okay. Yes, sir.
So
So like
again,
both of
yeah, please.
sir,
Please
if
tell me.
both of them are normal means like I don't get it. But if one of them is not, one of them are normal means we can do these things, right?
Yes, one of
Yeah.
them normal, HK becomes a subgroup. Clearly.
Yeah, got it. Thank you, sir.
Anyone have doubt? See, we are increasing the complexity step by step, one by one. Step by step, we are increasing the complexity. We start from what is group, but these techniques are so good. There is one more technique. This technique I never taught anyone. There is one more technique which is called a group action technique. Unfortunately, you should have a very good idea about the group action. Group action, same as permutation representation, then we can play even more deeply. Okay. Anyway, when you are doing PhD, they will tell you, no problem. When you are doing good PhD, they will tell you. So you got the idea. Now we solved all 10 of, like almost all 10. I mean, yeah, some of them are easy. At least see, this is a hard. This is the thing you need to know, group action. So I left it. This is done. This is done. This is done. This is easy. You can do it. This is, at least this is easy. This is what I taught in the group. This is Michael Martin book. Okay, M. Martin. It is very nice. Please read product group. Okay, I think 64th page in the second edition, page number. Okay, so this is we answered in general. In generally we answered. So we got everything. Yeah. So this is the 10th one is very special. So in fact, we proved that every group of order 30 actually has a subgroup of order 15, which is a specific section in Ď book. Okay, please go through your Ď book. That is what I'm expecting from you. You just need to follow receptive. Go to the Ď book. He proved that order 30 as a order 15. To say something about order 30, to classify order 30, we need order 15 somewhat. Okay, fine. So we got the idea, right? So 10. So additional question I added, but before that, we want to take other direction. So other direction means so far we played very much. So other direction means you should also have some good exposure towards the general linear group of finite fields. That is the reason. So now we are taking a step to understand this particular question. So far, whatever I solved mostly came in CSIR, NBHM, and like CSIR many times, in NBHM many times, TFR. It is like an entrance level exam. This is the particular interview exam which is asked by Professor K.N. Raghavan to my friend when he came to IMSc for his integrated PhD interview. This is the question. Okay, somebody read this question, please.
Let FQ
Let
FQ be the finite field.
Okay. Yes. Continue. Someone.
Let FQ be the finite field where Q is equal to P raised to alpha and P is the prime number. A. Calculate the size of GLN FQ in terms of Q. B. Show that at least one P subgroup of GLN FQ. Show at least one. And C. Calculate how many P Sylow subgroups are possible.
Okay. So now it is about finite field. If you have some little bit of that, that's why in the section started, I was telling, no, if you are BSc, you may not get it. That's okay. That's why I did it that part, the number part. If you are like little bit of in the end of BSc, you may get it, but in the first year, second year of MSc, you will totally get it. Okay, what is FQ? FQ is a finite field whose order actually P power alpha. In fact, in field theory, that is a thing. Every finite field should be prime powers. It cannot be a composite 2. Like order 6 is not possible. 2 into 3, no. It should be a single prime power. Okay, we are not going into that, but now the question. What is GLN of FQ? This is nothing but n cross n matrix entries from FQ. Okay, entries from FQ. If you are feeling like very hard, you can think of F2, which is like plus or minus 1. Okay. Sorry. That's not a correct representation. Representation is 0. So filled with the 2 order. Filled with the 2 order. 0, 1. So GLN of FQ means, so GLN of F2 means n cross n matrix with only that things. Okay, fine. So now the question, calculate the size. Definitely it's going to be, so how much possible? Q, maximum Q, each and every entry. So let's go for 2 cross 2. There are places, combinatorically, it is bounded by Q power 4. Why? Q choice, Q choice, Q choice, Q choice. So it is definitely finite. Can we get exactly? It is a matrix plus invertible. I could say that determinant of that matrix is not 0. That's a better thing. So it is a matrix whose determinant is not 0. Okay, GL and FQ is a collection of n cross n matrix whose entry from Q and the determinant is not 0. So now the question, first question, can you say the size, the cardinality? Okay, very good. This is actually a group, very nice group, which is called general linear group of FQ. N-fold general linear group of FQ. Okay, so what is the size? Okay, fine. So if you are good at linear algebra, you can get it. If something invertible, like something invertible, what happens that column wise, okay, look at the column wise. If you see like a column, this is like a vector. 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 So each vector should be linearly independent. That is from us, from linear algebra. So I'm going to fill the first one. Fill the first one. Forget about the second column. First column. I can fill anything. I can fill anything. I can fill anything. I can fill anything because the second I'm going to be careful. But the only problem, I cannot fill 0. If it is 0 everywhere, you know that no, if you take the determinant plus minus, everything 0, you will get the 0. So I cannot fill the 0. So I can go, there are n places. So Q power n possibility I can go except 1. Which is the one I couldn't go? I shouldn't go for 0. If it is 0, 0, 0, 0, then easily the determinant becomes 0. So I can do it. Sorry. The second column, once the first column fixed, the second column, I have to be very careful. Why I should be very careful? There should not be linearly dependence. It should not be linearly dependence. So I can fill anything, but removing that Q. Because if I choose 1, I should not linearly depend on that. Okay. FQ size is Q, which is P power something that we will come later on. FQ. This is GLN of FQ. There is a one vector I filled. The dimension of one dimension, right? One dimension. What is the size? If V is a vector space and I have taken a V and dimension 1, this is cardinality is base field. Base field is dimension 1, same as any vector. So Q elements I can go. Here I can go that many elements. But if I fix one element, I should not repeat that element, not only that element, that combination. 0 of that, 1 of that, 2 of that. Those are the Q times I could not repeat. So I'm removing Q. So the next column, okay. 2 things are done. There's a dimension 2. I can fill anything but Q square. Why? This alone Q, this alone Q. That will give you dimension 2. Dimension 2 is F cross F. In our case, FQ cross FQ, which is Q square element I should not fill. Similarly, I can go. That is the formula. The formula is first Q power n minus 1. 0 I should not fill in the first column. In the second column, Q power n minus Q. If I fill the first column, I should not repeat with a Q times. Linearly independence to be. The next one, Q power n minus Q square. First two filled, those will form a two-dimensional thing. I should go two-dimensional is q square in our case. I should go outside. Similarly, one can go up to, if I go for the third one is 2. Final one means, so that is the thing. So it is product q power n minus qk. The n is fixed. K is varying over 0 to n minus 1. That's a charted notation. Okay. For example, for 3 fq, this is the one. Okay, fine. Construct a p-Sylow subgroup, right? So far we worked with q. What is q? P power alpha. So far we worked with q. What is the size? G, L, N, F, Q. The size is q power n removed 1 because of 0. Q power n q dot 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 q power n minus q n minus 1. This much. Now you have to replace in terms of p. P power n alpha minus 1. P power n alpha minus p power alpha dot 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 p power n alpha minus p power n minus 1 alpha. Correct? So look at here. From here I can extract p power n minus 1 alpha. I can extract that much p. From the next one, so let me write it, p power n minus 1 alpha. From this I cannot extract anything. From this I cannot extract. From this I can extract what? P power alpha. So I cannot extract, I'm just putting 0. Just to note, I cannot extract anything, so p power 0. Here p power alpha. So next one, p power 2 alpha. Dot 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 this much. That is equal to p power n minus 1 plus n minus 2 plus dot 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 plus 1 into alpha. We know the formula now. First n minus 1 natural number. N minus 1 plus 1 by 2 alpha. Am I right? So far I'm right?
Yes, sir.
So I extracted maximum here. I extracted maximum everywhere. Here also 1. This is a p power 0. So something will come. Okay, what is that? P power n alpha minus 1. The next one, I extracted p power alpha. P power n minus 1 alpha minus 1 plus dot 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 p power alpha minus 1. It will reduce from n to n minus 1 up to alpha. This is the extraction. So this is the actually the p power something, the thing. This is the m. So let me write it very clearly. What is the clear thing? Okay, here which is written. This is the p. The p power, no? N into n minus 1 by 2 alpha. The remaining m. The remaining m is needed when we go through. So first, what is the next question? Show that at least, okay, at least one p-Sylow subgroup. Again, if you are really good at linear algebra, you can get it. Have you seen this number somewhere? N into n minus 1 by 2. Somewhere in linear algebra. Please tell me. Okay, specifically I'm asking. In matrix.
Dimension of symmetric matrix.
Very good. Very good. Dimension of symmetric matrix, Q symmetric, something related to that. So basically, symmetric matrix means somebody really getting the idea. Symmetric matrix means if you fix something here, this is fixed. If you fix something here, nothing is fixed. Nothing is fixed. Nothing is fixed. But if you fix something here, this is fixed. So if you fix, this is fixed. If you fix this, this is fixed. If you fix this, this is fixed. So this is like 1, 2, we are in n cross n, 3, up to the just before the diagonal, n minus 1. So basically, in the symmetric matrix, somebody really telling me good idea. This is 1, then is fixed. 2, then is 2 fixed because of symmetricity. If something is fixed here, this is fixed. Then I can go, forget about the diagonal. Let me use different color. Different color, diagonal. So this is fixed. I can go n minus 1. Nth time the diagonal will come. Diagonal won't give you any fixed, only in the diagonal. And my something suggesting me, I can be free here, I can be free here, I can be free here. I should not be free here. Something suggests me, if I go, I should not be free here. And remember that at the same time, what I want the invertible matrices. So something telling me I can be free everywhere, not here. And something telling me I want the invertible matrices. What is the best invertible matrices that we can think of? Something I can free, that not free here. So the best invertible matrix is, to check it, better to go upper triangular matrices. So I can be anything, I can be anything, I can be anything. But here, for the sake of simplicity, let me put 1, 1, 1, 1, 0 everywhere. Is this a invertible matrices? Yes, because diagonal element I'm getting 1. So it's a determinant 1. This is the invertible matrices. Good, really good. Invertible matrix. Downside. This is upper triangular matrices. But what are the free? I am free here. I am free here. I am free here. So this will contribute p power alpha. This will contribute p power alpha, p power alpha. This will contribute. Finally, it will contribute p power n minus 1 into n by 2 alpha. Am I right? You see, that is the comfortability in combinatorics. You have to have a little bit sense of combinatorics to enjoy it. Am I right so far? Is it okay? You no need to expect to match my knowledge because I'm very ahead of you. I know a lot of things. You will also know lot of things more than me once you reach my age. My age is like more than 30, right? So it's okay, no problem. But can you able to at least verify, am I not doing any mistake, right? I'm not doing any mistake. Fine. So I showed you one Sylow. Okay, so where is the one Sylow? Forgot. So this is the one Sylow, like the matrices. Somewhere missed. In the notes I included the structure. Somewhere I missed here. The structure is 1, 1, 1, 1, 0, 0, 0, 0, anything. So they will put it like this. Anything. So this is the one P Sylow. The next question is actually how many of them? So we know how to do how many of them. What is that thing? NP congruent to 1 mod P. NP divides the remaining. What is the remaining? The remaining is P power alpha minus 1, P power 2 alpha minus 1, P power n alpha minus 1. This is the remaining. This is little bit difficult. So what I did actually, I included in the notes the reasoning, very short reasoning. Okay. To do this, you need to understand what is called normalizer. Normal subgroup is fine, but normalizer little bit difficult. That is the point you need group action. Okay. Please see one of the video I done group action techniques, which is uploaded by Vinod sir, which is there in YouTube. In my name, you can see that. Okay, there is a playlist. Maybe Vinod sir can create a playlist in my name. It is there. You have to understand what is normalizer. Once you understand the normalizer, you can do it. Now I'm giving you the idea to do what next. I will give the notes to Vinod sir. He will circulate. Understand that, and you try to read what is normalizer, what is stabilizer, what is orbit from the group action. Then you get this idea. So what exactly normalizes this particular group? It matters, right? So that is the idea. You do it, okay? So let's stop here. Let's go through some of the additional questions. I posted some of the additional questions here. So it's not here. Yeah, some of the additional questions here. This one is very good. This is one of the examples for 12. You can start, okay? Try this. This is the question in CSIR. You see they ask something. GLN of FQ, right? GLN of FQ. They asked. And another question from TFR. GL3 of F5. They asked. You know what to do. What is this? This is nothing but Q3 minus 1. Q3. So 3 cross 3, right? Minus 5. Q3 2. So this is like 125 4 into what is this? This is like 5 125 125 120. This is 100 100 something like this. You are getting, no? Okay. So the next question, true or false, it's about silos. You can do it. I'm sure that you can do it. Try to find, and the answer is actually false for this. The answer is true for this. Okay. This one is very nice. Fifth one. This is a theoretical question. Whether you understand the idea, and remember that I will give you the hint to do this. But I want you to go through M. Artin book. The second Sylow's theorem, I told you, it's not complete. There is a partial statement. Okay. The statement of second Sylow's theorem, what we want, we did it. But the full theorem is actually every P subgroup inside P Sylow subgroup. It's like every ideal inside the maximal ideal, like that. Every P subgroup inside P Sylow subgroup and any two P Sylow subgroup of conjugate. This is the complete statement that you need to understand this fifth one. Look at the seventh one. FP GL of 50. You have to just calculate. What do you need to calculate? The order of P Sylow subgroup. We know, no? What we know? It is P power n minus 1 into n by 2 alpha. Here the alpha is 1 because the Q power is nothing but P power. P is 1, power is 1. So it is nothing but we need to calculate n into n minus 1 by 2. What is n here? 50 into 49 by 2, 25. So you just have to calculate and understand that this one. So what I do, no, it's very simple. Sometimes I do in the exam like that. So 25 is going to end with 5. That's it. Because 25, right? There is an odd number. It's going to end with 5. So I'm just putting this, not wrong. It's not going to end with 3, definitely. It's not going to end with 0 because a odd number and 25. So there is a 5 with an odd number. So I can think of like that. I mean, with due to the experience, okay? So please try these things. I will give you the notes, okay? So let us stop the class here. So we can stop the recording also. And I will talk a little bit after the class, okay? Thank you.
Okay, thank you, Jay, for this nice session. Now we will move to the feedback session. So dear participants, feel free to share your feedback about the session, and also you can ask any queries.
Let me come from computer.
Yeah.
Hello.
Yeah.
Can I send these notes in this?
Yes, Rashmi Singh. Yes.
Yes, I
Yes.
keep.
Yeah. Yeah, Rashmi Singh, you can. Okay, dear participants, you can share your feedback now. Yes, Dharmendra.
Yes.
Dharmendra.
Good evening, sir.
Good evening. Yes.
Yeah.
It is a nice session, sir. Thank you for organizing this. I'm looking forward for more sessions like this. And Jai sir, like your unique way of that pessimist way and counting, like relating things is very good. Learned new things, sir. Thank you.
Yeah, you will have something called optimistic. Okay.
Yeah.
I will tell you one more thing to understand this pessimistic optimistic. You know basis in linear algebra, right?
Yes, sir.
So there are characteristics for basis. It is a minimal linearly independent set.
Huh.
From
Yes,
that,
sir.
it's like an extension which is called the optimistic way. And also, sorry, maximal linearly independent set. So that it is from simply it's gross. It's an optimistic way. Also, it is a minimal spanning set, which is a pessimistic way. Where this pessimistic optimistic meet, that is the place called a reality. That is the exact definition of basis. Okay, minimal linearly independent, maximal linearly independent, minimal spanning to meet at some point. So the person with the reality will see the both possibilities. Okay.
Okay, sir. Like we know this, but realizing it in a unique way is.
Yeah. So I will give you one more example languagically. So if you are like Malayalam or Hindi or English, so other than English, I will give you 4 words. Try to convert into your language and you will see the problem. For hope, faith, belief, trust. For me in Tamil, there is only one good word. All these things collide into one good word. So somebody converting that into the some other language, it will collide. Again, if you go back, you will lose it, right? So that's why we need to see from the both end. So try to understand from an optimistic way also. Today, I really take pessimistic way because I like Buddhism. That's why I took it. But optimistic way also really good. That is what they are doing in your class.
Okay, sir. Thank you.
Nice.
Okay, thank you, Vandana. Could you introduce
Excuse me.
Vandana? 1 minute.
Yes, sir.
Yeah, please.
Like, sir, I did my MSc from University of Hyderabad, and now I am doing doing as research intern in Geetham University, Bangalore.
Okay. Thank you.
In commutative algebra. Thank you,
Yeah.
sir.
Okay.
Oh, nice.
Yeah. Yes, Deepak.
Sir, actually, the session is really nice. The way of approaching a problem and telling what the problem really means and what it is teaching us and how to solve the problem, what are all the things that we are getting from a problem. So everything is really nice. And today I have learned something like way of approaching a problem. Like if there is a, if we want to approach a problem, means first we have to understand what are all the things is given and what are all the things are asked and how we can like eliminate something. So I have understand many things and some important theorems like thing and understanding the like some words sir stretch the thing. Like at that time I can understand how a mathematician really felt while explaining some mathematical concepts to someone. So it really connects me emotionally, as well as it is really nice to hear such thing. And still now I like analysis, but I'm not that much interested in algebra. But I'm sure that after this class I'm really interested in algebra, sir. So that's really nice thing. Yeah, thank you so much for the session, sir.
Nice. Thank you.
Thank you, Deepak.
Pleasure is mine, sir.
Hi, sir. I'm Amrita. Actually, I must appreciate you for taking your time from a busy schedule. It was an amazing session, especially the using of the Sylow theorems to find the normal subgroup of order 5 in group 30. It was really amazing. I never knew we could do it in a very, as you say, the pessimistic way. It was just mind-blowing, actually. I was just smiling throughout the session because I never knew we could apply Sylow theorems in this way also. And thank you so much, sir.
Yeah, thank you. Yeah, these are the things, you know.
Thank you, sir, for your wonderful session. It helped me a lot as I am teaching in a college, local college, so and also preparing for PhD for PhD entrance test, and
No,
and it's such a unique way. So I would try to apply it in my teaching as well, if I could do positively. But I will try someday. So thank you so much, sir. It cleared a lot of my doubts. Thank you, sir.
You know something? I just please introduce. Deepak also didn't introduce yourself. Please introduce. But I want to say something. You must have heard Lam, right? That one who is evolutionist, who conducted studies of evolutions. Charles Darwin.
Yes, sir.
Yeah, Charles Darwin saying that mathematician is a blind man who searches for the black cat in the dark room. Try to understand this. This is very much, you can take it as an insult, or also you can take it as in a different way. Mathematician is a blind man who searches for the black cat in a dark room. So it's kind of insulting at some point. But if you take it from another view, mathematicians trying something impossible, right? So searching a black cat, a blind man in a dark room, is like saying nobody dare to try. Nobody dare to try means if you are even with an eye, you don't go to the dark room to search for the black cat. Even if you try to go to the dark room, you don't dare to attack to see the black cat, right? So you will see that if it is a white cat or some other cat, we could try, but black cat. But he is also adding mathematicians are blind. So in some way, mathematicians are realistic. Today, I took the optimistic view. As I said, negativity is more authentic because there are books to how to love, how to parenting, how to be happy, how to be regards, how to do this, how to do this, all. Do you see any book how to be hateful, how to get angry, how to get jealous? And if I ask you people, are you in love? Are you in regards? You may not say like, I don't know. It feels like that. It feels like that. But when I ask you people, are you in angry? You will definitely say whether you are in angry or not. Are you mad? Yes or no? That's the answer. So somewhat negativity resonates us. Out of the negativity, positivity comes. That is a realistic idea. That's why I took it very personally. Okay. This is one of the reasons. Please tell me from where you are from. You are saying that you are a teacher, right? So please tell me where are you from? Also, Deepak, you also tell me. Just wanted to know. Somebody said that they are from Bengaluru. I was there in Bengaluru like 2 weeks before. I also thought that I will give, you know, directly go to the classes, colleges, and talks like this, live talks. If the colleges agree, I can contact you people. Yeah, please.
Sir, I am Simmerpreet Kaur. I did my post graduation from Central University of Punjab. I am from Punjab only, and I did my post graduation in 2022. And after that, I cleared NET JRF in my first attempt, and then I got a job in a local college. But now I am planning for PhD.
Nice.
So I'm preparing for that. So I'm just being just a beginner. So I'm just a learner as well. So I'm not a teacher. Well, I won't call my as a teacher. Being a teacher, I am also learning. So I'm always looking for better and better methods for and like a different point of views for looking upon a same problem. So so the thing I learned today is completely new that I was. I was not. It was like thank you so much, sir, for the for this point of view. And it was such an amazing session, sir.
Thank you. This kind of words encourage me to give more classes. Nice.
Yeah, thank you. Thank you, Simmerpreet Kaur. Actually, our platform is for people like you.
Sir, this is Vandana
Good
from
evening, sir.
Bangalore.
Hello.
Yeah. Yes,
Uh,
Vandana.
Sir, like we get to know about your session on the same day around 9 o'clock. So
Oh, I
we
see.
tried to attend, but we could not make it.
Which one?
Like in IISc Bangalore, I think.
Oh, okay. Okay, I see. That's okay.
Okay.
But when I stayed there for 1 week. The fourth day, third day, my talk over the research talk. I thought of I will go and give some local colleges. I asked my friends. None of my friends are, as sir mentioned, no. It is very hard to get resource person. None of my friends are known there. But in my Chennai, Chennai, I used to go to the colleges, local colleges, if I get a chance. So that actually motivates me to give something like this. So why don't we do all over India? In Chennai, it's very easy, local language. I feel like it's comfortable talking in Tamil, but I wanted
Hello.
to explore the thing also. Yes, please. Veera
Hello.
Parthiban.
Veeravatran, sir.
Veeravatran.
Sir. Sir, I am Veeravatran. So I am pursuing MS Mathematics in Chennai Vivekananda College.
Oh, super.
Yes, sir. So your session is very useful, sir. So I understanding the Sylow's theorem, Sylow second Sylow. So and also your way of teaching is very nice, sir. So
Okay, that's
I
coming
thank to
from directly from someone called Tilopa. I adopted that area thing. It's that pessimistic approach. So I want you to say again, pessimistic never means negative. Okay, please. If you go to the other people, they will say pessimistic is not negative. Pessimistic is a possibility of unfavorable choices. Not possible like that. Okay.
Okay, sir.
Yeah. So good.
Okay,
Very
sir.
good.
Okay, sir.
Maybe
I thank to
I
you
will put you to the college.
and also the notes, sir.
I'm requesting Jayakumar sir to come to the college. Soon I will come and directly give some lecture.
Hello.
So you had actually forgot to introduce myself. I'm Amrita, and I'm doing my BSc third year in 𝕨𝕬𝕝 College, Chennai. So
yeah, if you have a chance, ask your HOD to get a
Sure,
possibility.
sir.
I will send a proper email for myself.
Sure, sir. Looking forward to it, actually.
Thank you. I will share my Twitter ID. There I'm sharing much things about math, also how to use AI to math. Okay. For example, in this kind of platform, share conducting, very hard to find resource person. Even there are good resource person not spending time. But let's say you have some doubts that you are not getting. You need to understand one word called edge. Okay. I'm writing one article to understand the one word called edge. Okay. I will tell you simply what is edge to understandable. So suppose you think of a crime investigation, somebody is suspect, they will put a lie detector test. No, that is not acceptable in the court. Okay, that is not acceptable in the court, but still they do. Police, why? To get the edge. If the lie detector says something, they can take the direction. In mathematics, actually, we have some good word for that. It's called guesstimation. Art of guesstimation. That is what I did in the last. Did you see what I did in the last? That is 25 into 49, right? I did not calculate. I took the chance of guessed estimation. Why? There are 4 answers. I can take the choice because I know this is a odd. Then I can give the idea. I did not go through. If I start doing that, it will take some time. So that is called the edge. You start perhaps. Okay, there is another good word. It's called in stock market. They call it edge. In our side, in math or science side, they call it perhaps. It's not maybe. Okay, maybe it's a weaker version of perhaps. Perhaps. So that what I'm trying, you have to strong in language also, so that you can break it. Okay, that is one of the good thing about me. I developed the thing about language, so I can share the language that enhances. It's like a butterscotch ice cream. There are little sugar ball or black currant with the thing. No, that's how I share. That's how I did actually. Try to understand from cost of guesstimation. Okay. Okay. So yeah. Sorry, I'm taking too much time. I'm sorry.
Hi sir, I'm Shyama Kumar. I completed my BSc from Aspirants University. Now I'm taking a gap year to prepare for MSc entrance exams. So today's session was really nice. As so many people mentioned before, the pessimistic and optimistic way of looking was very new to me also. I really enjoyed the session, and also I was familiar with some theorems, but I got to know the proofs today, and it was really interesting. Thank you so much, sir.
Information, confirmation, transformation. Statements are information. By understanding the proof is confirmation, but that is not enough. To transform, you attack the problem. This is what meditation about. But math, it is easy. Statement, proof, apply. The people who know math, they can live three-dimensional. Okay, remember that. Yeah. So any more feedbacks?
Hello, sir.
Ankit Mayuriya. Yes.
Yes, sir. I am, sir, BSc third year last year, and I am preparing for master IIT JAM.
Yeah. Oh, you introduced no feedbacks. Okay, fine. No, good. That's good.
Okay. Yeah. Any other would like to share any feedback? I think
Somebody have a DP of somebody. Yeah.
Yeah, Alaika. Yes.
Sir, I'm a final year BSc student from Kerala, and almost half of the topics that you taught today are new to me, and I have only reached half of my subjects till now, so almost most of them are so new to me, and your session was so good because even without knowing, understand what you are saying. So thank you, sir.
Thank you.
Okay, thank you, Alaika. Yeah, once again, thank you, Jay, for this nice session. I hope that you will be there to have more sessions in our platform.
Definitely, definitely. I'll continue this algebraic approach.
Yeah, also I request you to introduce more resource persons like research scholars in your institute or any other premier institute to take such sessions in our platform.
Yes, I will try. Please do again. I'm telling one thing. In Twitter, you have a Facebook. I think Facebook is different. Facebook is Instagram are different. Twitter, there is something called verification progress. Any good content creator cannot use like a fake accounts. Okay, for myself, I have a verified account. To verify, we need to pay something like that. But one good thing about the Twitter, that is not fake. Most of them are verified. Good content creator. There are very good math people. There are very good AI people. There are very good philosophical people are there. I am following some of the AI people and math people. From them, I'm getting lot of good notes they are posting. Like there is a one guy called Alex Brazilian. He is posting about Terence Tao. Simple ideas how to write one page. Terence Tao somewhere posted somewhere. It is not famous. He is posting again here, and he's giving the idea. He's not telling anything from himself. He's posting and reposting. Okay, that you can understand. That is really inspirational. That from that only I'm getting the idea. One. Second thing is that you can also follow me. There is lot of things about AI, how to use AI to math, like how to use AI to write notes, how to get the bug fixed. There are some problems. For my notes, I used some backgrounds and other thing. All I'm using from AI. Those are free. AIs are free. Okay, but get to know. See, kindly follow me in Twitter. I will share the link with the sir as well as here. Please follow me. Then you'll get more of them. Okay.
Yeah, we can share the link with the recording of our program.
Yes.
So please do, Jay, please do share the PDF of today's session also.
Yes, I will share by 10 or 11, before 11.
Okay. Okay, thank you everyone. Let us wind up here.
Okay, so bye.
Okay, bye. Good night.
Hello, excuse me. Am I audible?
Yeah, yes.
Yeah. Sir, where may I can get the recording and PDF? So, actually, it's for the first time I am here.
So, Simar, did you join in Math Aspirants group?
No, sir, I am not a part of that group.
Okay, you can just WhatsApp me. I will give you my number in chat.
Okay, thank you, sir.
Wait, I am typing it here. Yeah, you can message me in WhatsApp so that you can. I will add you to our WhatsApp group. this type of information about our sessions as well as other math related things will be shared in that.
Thank you, sir. I was looking for this such a sort of group where I can get good resource persons, and thank you so much, sir.
Okay, Jay, let us wind up here. Bye. Good night.